Hello and welcome back. Now, I'm going to spoil this video ahead of time for you. Nothing in this video is required knowledge for a test. I still think the stuff in this video is really interesting, so I encourage you to watch through it, but you're not going to be tested on it. All right, what we're going to talk about is a bunch of different types of batteries. We're going to talk about corrosion and other things. So, what do we have here? We have a fuel cell, and we talked about that. We said, hey, look, when we take water, we split it into hydrogen and oxygen. When that runs again, we get lots of energy out. We can use that heat by just running the reaction, getting the heat, but we can also split it up and use the electrochemical reaction in order to get energy out. And that's what a fuel cell does. It splits up the hydrogen and the oxygen, allowing them to react to make the water in there, but also to get that electron out, which can do things like run an electric motor. So the reactions there are very similar to what we just saw in our previous video, so I'm not going to go over them too much, but that's all a fuel cell is a little battery. Okay, our next one, lithium-ion batteries. You've heard of these before. So there's secondary batteries, which are rechargeable, but there's also what we call primary batteries, which are not rechargeable. So we're going to talk about the rechargeable lithium-ion battery, what's called a secondary battery. And what you have is you have lithium in graphite. Now, why do we use lithium? What's so interesting about lithium batteries? How come we don't get potassium batteries or sodium batteries? The reason we use lithium is because it's tiny, right? It's the third element on the periodic table. It's really, really small. And because it's really, really small, it can migrate relatively easily, even in a solid phase. And so what happens is our lithium at our anode gets oxidized to form lithium ions. Okay, so those lithium ions can then actually migrate over here to my cathode side. On the cathode, you've got a lithium and manganese complex, which reacts with the lithium ions to make lithium and manganese solid complex. So you're basically changing the stoichiometry of that complex over time. Right? Now, overall, you get that bottom reaction there, and you get about 3.7 volts out of this. It's a very high voltage reaction. It can run relatively quickly because lithium can migrate fairly quickly through that electrolyte, which is why we like our lithium-ion batteries. Then when you plug your iPhone into the wall, you're putting in 5 volts against that, and you're just forcing the lithium ions to go backwards through your battery and go back over into the graphite side. Now, why can we not just charge lithium-ion batteries forever? Right? What's wrong with this picture is that lithium does get stuck. Right? So sometimes it'll get stuck somewhere. Sometimes there's what we call unwanted, undesired reactions, side reactions that happen. So the lithium or the manganese can undergo other reactions as we're either using the battery or charging up the battery. And all of those things add up over time. And we find that batteries, right, your cell phone battery after about a year or two starts to be like, wow, I just charged it this morning. It's only 2 hours later and the battery's almost dead. Because over time, all those side reactions and the lithium getting stuck and things just make it so you don't have as much ability to move things around in there. Okay, our standard AA batteries, AAA batteries, we call those the alkaline dry cells. And there's also quadruple A batteries. They're really cute. They're really tiny. Okay, they're not rechargeable because you end up using a zinc oxide and manganese hydroxide, and they can't diffuse. These are big, big molecules or big, big atoms. They're not going to diffuse through our system very easily like the lithium does. So what happens when we're running our battery is at the anode, zinc gets oxidized to zinc oxide, producing 2 electrons. And the cathode, manganese oxide, gets reduced to manganese 2 hydroxide, manganese 4 oxide to manganese 2 hydroxide, and you overall get that reaction, and you get about 1.5 volts out of your cell. Now, if you look at the actual organization of it, you've got the zinc anode on the outside. That's this green part here that I'm coloring right now. You've got a separator between that and your manganese hydroxide, which is your cathode. And then you've got the different parts. The negative end cap is in contact with the zinc anode. You've got a graphite rod in there. Graphite, remember when we don't have a conductor built in, because oxides are not generally conductive. Hydroxides are not generally conductive, so we need to have something built in that's inert but also conductive, and that's our graphite, which then goes up to the top button here. All right, so our negative end cap is in contact with our anode, and that's one thing to remember about batteries. Our negative end cap is in contact with our cathode, or sorry, our anode, because it's producing electrons. So the part that's producing electrons, the part that's producing electrons is where our anode is, and that's our negative side. And you can think about that because it's producing electrons, it's negative, and then the positive side is where the cathode is because it's accepting those electrons. But one interesting thing I think to point out about the alkaline dry cell is that generally when over time they tend to explode, right? So the battery gunk oozes out. What's happening there is, again, these side reactions that happen as you're running the battery. One of them generates hydrogen gas. And so what happens over time is pressure builds up inside there, and eventually it does explode. Now it explodes kind of, slowly and nicely. It's not poof or anything, thank goodness. Okay, but it does eventually explode, and the contents ooze out. What are the primary contents? It's manganese hydroxide in a potassium hydroxide, manganese 4 oxide in a potassium hydroxide paste. So when that happens, the general phrase that we talk about is, oh, the battery acid's leaking, or, I got battery acid on me. But it turns out in an alkaline dry cell, what's actually leaking is potassium hydroxide paste, not an acid. So what's actually leaking is battery base, not battery acid. Okay. We get the battery acid from car batteries and other types of batteries that do use acid, but in this case it's actually in a potassium hydroxide paste. Okay, little tiny button batteries, those are very similar to what we just talked about, except those generally use either a silver paste or a mercury paste, not too much mercury anymore, so most of these are just silver, where silver oxide turns into solid silver at your cathode, zinc gets oxidized to zinc oxide at your anode, and you get about 1.6 volts. These things are very, very nice because you can put them in very, very small spaces, and they're still produced about 1.6 volts. But they're a little bit dangerous because kids think they look like candy, and so they swallow them sometimes. But very similar chemistry to what we saw in our AA batteries. The next one is the primary lithium battery. Right? It's not rechargeable, and they do make these. Why do they make these? They make them because they can produce a large amount of current very quickly, and they can produce relatively large voltages of them by stacking these batteries one on top of the other. And so each one of those little kind of sheets that you see in there is one battery stacked on top of the other, and so you can put a whole fairly high voltage, high current battery in there. One very interesting thing about these primary lithium batteries is, you see this down here, you have O5.5 as your formula. So you've got silver, vanadium, and oxide with an O5.5. You've got 3.5 lithiums reacting, producing 3.5 electrons. It's very interesting. These are what are called non-stoichiometric compounds. And they are things where the crystal structure at a very, very fundamental level is there is really only half an oxygen in one crystal, and there's half an oxygen sitting in this other crystal, and if you try to interpret it any other way, it doesn't really work. And so we get these funny little non-stoichiometric compounds, which is kind of a cool thing. The next one, the lead storage battery. This is your car battery. Your car battery is lead and lead sulfate. So at your anode, your lead is turning into lead sulfate. At your cathode, lead oxide is turning into lead sulfate. That's interesting. Both sides are making lead sulfate. When you run it back, when you run your car, it's charging your battery. It's using the extra energy from your engine in order to charge your car battery, and you've got lead sulfate turning into both lead to lead 4 oxide and lead solid, and that's called a disproportionation reaction. We have the same compound, our lead 2 sulfate, being oxidized and reduced, once to lead 4 oxide and once to lead, and then we can run the thing over and over again. Now, you'll also notice with your car batteries that over time your car batteries start to fade. They don't work as well, even though nothing in this reaction would tell you that that's going to happen. The primary method by which car batteries fail is side reactions somewhat, but the primary method is that lead 2 sulfate is actually very, very flaky. Lead very malleable, very easy to work with. Lead oxide, very hard. You're not going to have too many problems with that. But lead 2 sulfate, very flaky. And so, you're driving your car down the road like this, and you're making some lead sulfate. What happens is that lead sulfate can fall down, right? It can actually like plate and flake off of your battery. And right as it does that, it's no longer usable because it's now sitting at the bottom. When you go to the battery store, right, you go to a car mechanic or Walmart or wherever you go to get your batteries, AA, AAA, right? They're going to ask you, oh, do you want the 1-year battery, the 2-year battery, the 5-year battery? And there's a big cost differential associated with them. And you may have wondered, what's the chemistry difference between a 1-year battery, a 2-year battery, and a 5-year battery? And there's basically no chemistry difference whatsoever. They're all lead batteries working on lead going to lead 2 sulfate, lead 4 oxide going to lead 2 sulfate, and then backwards again. The primary difference between those different batteries is how much space is on bottom to catch the lead sulfate before it piles up enough that it short circuits your battery. Okay. Yes, there's a little bit about how much material there is and things like that, the thickness of it. But one of the primary things is how much space are you paying lots of money for? And even though you know this, even though you know that the 5-year battery just has more space on the bottom to catch the lead sulfate than the 1-year battery, it's not like you're going to go out and make your own battery. You still have to chunk out that money for that 5-year battery. I generally kind of go in the middle myself, somewhere in the 3-year battery, and most of the time that works for me. All right, our next thing is corrosion, which is redox gone wrong. Right, just like in your garden, a weed is whatever plant you don't want to grow. For somebody else, it might be a desired plant, but for you, it's a weed because it's the plant you don't want to grow. Corrosion is just redox that you didn't want. And so we're going to talk about different types of corrosion very, very quickly. I'm not going to spend a whole lot of time on this section, right? But it's just oxidation of a metal is generally what we consider to be corrosion, okay, by strong oxidizing agents. What are the strong oxidizing agents that we run across? Oxidizing, right? The primary one is oxygen. So, right, the oxygen in our air is a very strong oxidizing agent, especially in comparison to metals. You can look up the cell potentials and find that most metals will oxidize. The reason gold doesn't is because it's got an oxidation potential that falls in a way that oxygen is not going to oxidize it, which is one of the primary reasons we use gold for things like conductors and stuff like that. Is not because gold is the world's best conductor, but because it is not likely to oxidize due to its standard cell potential. Okay. Chlorine, if you've got chlorine around, that's going to oxidize things. Nitric acid is going to oxidize things. Okay. Rusting is a very specific type of corrosion that's generally talked about only with respect to iron. Okay. And it's a process that we'll talk about in just a moment. All right, so gold, you look at these standard reduction potentials. Here's oxygen, right? Likes to be reduced more than just about every metal except for gold, which is again why gold doesn't get corroded by oxygen, but most other metals do. You'll also find that mercury doesn't, even though its standard cell potential would say that it should, and that's an overvoltage issue, is that there's just not enough voltage available or energy available in the standard room temperature to oxidize mercury in the presence of oxygen. But pretty much every other metal does. I mean, you look at aluminum down here, huge driving force. Okay? And you're never in your life going to touch aluminum. You're like, yeah, I touch aluminum all the time. I buy aluminum foil at the store and I can touch it. And it turns out, no. The reaction of aluminum and oxygen is so energetically favorable and so fast that the moment aluminum is exposed to oxygen, it immediately forms an aluminum oxide layer on top. So when you touch your aluminum foil, all you're touching is aluminum oxide. And you're like, okay, let me tear the aluminum foil and use that fresh little strip right there. As you are tearing it, the moment it is exposed to the air, it is so reactive with the air that it forms an aluminum oxide layer. And so as you tear it, even if you put your thumb there, right there, you're touching aluminum oxide. Because look at that driving force, minus 1.66 volts as compared to 1.23 volts. That's a huge driving force. One interesting thing is if you break down the periodic table, you can kind of see this kind of almost periodic table shaped thing. The stuff over here on the top left tends to form oxides. So when you react it, it'll tend to form things like oxides. So iron oxide, copper oxide, other oxides. But down here on the lower right, it generally tends to form these sulfides. And so you'll find things like mercury sulfide and silver sulfide. So when you see silver that's tarnished, you're, yes, looking at corrosion of silver, but for the most part, you're actually looking at silver sulfide molecules, not silver oxide molecules. Where does the sulfide come from? It's naturally present in the environment. It's also exacerbated by homes that use a lot of natural gas. They add a lot of sulfur compounds to natural gas so that it smells. Natural gas is naturally odorless. So they add those sulfur compounds so we can smell it and detect that it's there, but then it corrodes certain things like silver and mercury a little more. Okay. Rust. Rust is a very specific case of corrosion, and it costs so much money. I mean, think of all the things just in your life that have rusted away over time, and extrapolate that to the world and to buildings and to all sorts of things, ships, right? How do we deal with the fact that rust occurs, and is there anything we can do? Well, the first thing we want to know is, what is rust? Rust is a two-step reaction where it turns out that rust forms in a slightly different place than the iron is taken away. You don't form rust exactly where you are corroding your iron. The corrosion occurs in one spot, then the iron ions have to travel to where they're exposed to the air on the outside of water, and that's where the rust forms. And so you actually get double here, as you get some pitting in one location, you get rust formation in a different location, and it only occurs in the presence of water. Dry iron is not going to rust. You need some amount of moisture in order to make it happen, and even some amount of acidic moisture in order to make it happen faster. Okay, so that's why you get different locations of the pitting and the rusting, is because that reaction to actually form the rust has to occur in the presence of oxygen, but the pitting occurs inside the water area. So how do you prevent it? One, right, you can coat things, you can paint it, right? But there's also a neat one called a sacrificial metal electrode. And what that case is you've got this big iron thing, right, and oxygen's coming in and trying to attack it, but it's an electrochemical process, right? So there's some electron transfer involved. So what you do, and since iron is very conductive, somewhere on the iron you're going to attach to it a metal that oxygen would rather oxidize. So if we go back over here, we've got iron down here to minus 0.44 volts. Right? So you're going to attach somewhere on the iron system something that a reduction potential of even less than 0.44 volts. You could attach aluminum, but it forms that protective oxide really, really quickly. So other things that people tend to use for what we call a sacrificial metal electrode are things like, I believe, magnesium. There we go. I almost said manganese, but it's magnesium. So magnesium would rather oxidize over iron. And so you attach magnesium somewhere, and it turns out those electrons reactions that occur in the iron, instead of the electrons being transferred to the iron, they're transferred over to the magnesium, and the magnesium will oxidize over time. Now that magnesium will eventually corrode enough that it's either A, not conductive, or B, it just falls apart. And so you do need to replace sacrificial metal electrodes over time. That's why they're called sacrificials, because they sacrifice themselves for the good of others, right, for the metal, for the iron. But it's a neat way of preventing corrosion by just forcing nature to corrode this other thing that would rather corrode more. And they'll even do that on metal pipes underground. They'll periodically connect these sacrificial metal electrodes to them and replace them periodically. All right, so that was all that I talked about. I wasn't going to actually show you the chemistry of that, right? You can just think about magnesium oxidizing instead of iron. So that was just a little quick overview of some batteries and some corrosion stuff. Like I said, not on the test, but hopefully still interesting nonetheless. Thanks so much for listening. Have a great day.